Today we're going to cover topic 6.1, which is circular motion. So today's objectives and applications and skills. Today we're going to talk about and define period and frequency. We'll also talk about angular displacement and angular velocity from a definition standpoint. And then we're going to talk directly about centripetal acceleration and centripetal force. Under applications and skills, we're going to need to identify the force that's actually providing the centripetal force. Centripetal force is really a misnomer. It's really the acceleration that is centripetal. The centripetal force is really just the net force. Obviously, we'll need to be able to solve problems involving centripetal force and centripetal acceleration. And also qualitatively and quantitatively describe what happens when in circular motion when it's not uniform. This is primarily vertical circles where it slows down and speeds up as it goes around the circle. In terms of formulas, we really only have one formula. All of these are kind of variations on that one formula, actually two formulas. The first formula is velocity is equal to omega r. That funny looking W, okay, this little W here is really the lowercase Greek letter omega. It stands for angular velocity, and we'll cover that equation. And then we have the centripetal acceleration formula, okay, that says acceleration is equal to v squared over r. We're fairly familiar with that. In another variation of that formula that we'll talk about, it's also going to equal 4 pi squared r over t squared. And I'll show you how to derive that, so we don't really need to memorize that one. And then last we have the Newton's second law formula, which is F equals ma. If I make a substitution for a, then I end up with F equals m v squared over r. Or making a substitution for v, I'll end up with m omega squared r. Under guidance, there's this term that's called banking, okay? And it says we'll only consider banking in a qualitative standpoint. We won't actually have to do calculations, but we will work through some problems so we understand what banking is. Banking is what happens when you're trying to make a turn and it's not on a horizontal surface. A lot of our road exits are banked, and it allows you to make the turn at a greater speed than normal. So first off, definition of period and frequency. Hopefully we're already familiar with these words, but we'll go over them again anyway. Period, we usually use the letter T to represent period, and this is the time required for the system to make one complete cycle. And the units for this measurement is seconds. Frequency is the number of cycles that the system completes in 1 second. The units for this is 1 over seconds. Later on, we'll also use the term hertz to represent frequency. So these two values are simply inverses of each other. So once I know one, I automatically know the other simply by taking an inverse of it. Okay, so period is equal to 1 over frequency, or another way to put it, frequency is 1 over period. So the rotational variables are what we're going to be using instead of our linear variables in this, as kind of as analogs to our linear variables. Okay, because when we're moving in a circle, what's going to be more important is the radius and the angle of the circle. Where are we on that circle? Those are the important variables. So instead of displacement, velocity, and acceleration, d, v, and a, as shown under linear variables, we're going to be using rotational versions of the same words, of the same descriptions. Okay, except for displacement, we're going to be using the Greek letter theta, and for velocity, the Greek letter omega, and for acceleration, the Greek letter alpha. Okay. These are all going to be in radians or radians per second, and I'll show you what I mean by displacement. Okay, so here I have a circle. I can trace out a whole circle here, and so as this thing moves around in uniform circular motion, if I start it from right around there, okay, at 90 degrees. Okay, but I continue moving around. So actually, since we're working in radians, let's stick to radians. That's pi over 2 radians. And as I move over to here, I've gone through a displacement, okay, from this point to this point. I've gone through a displacement. Whoops, it didn't actually click. Okay. Okay, so going from that point to this point, not actually clicking for some reason. Okay, so I'm going from A to point H, okay, and what I've done, okay, is I've gone through effectively 90 degrees, okay, so here I am at A, and then I continue all the way over to that letter, and so now, I'm not quite sure what's going on there, but I've gone through 90 degrees of displacement. I can basically do that and, continue and go through 180 degrees of displacement from point A all the way to 270 degrees of displacement, okay? Just like with velocity, I can have negative displacement, okay? So if I go all the way down to, say, 45 degrees, at 45 degrees, I have negative 45 degrees of displacement, okay? So that's what rotational or angular displacement is. How many degrees difference? Okay, I can certainly have more than one circle worth of displacement, okay? Especially for things that roll like a tire. If I roll it several times, then I've gone through more than one circle worth of displacement. Okay, in terms of angular velocity, it's basically how quickly am I going around this circle? How many radians per second am I going? Right now it's fairly slow, so I'm not going to have too many. My velocity is slow, but I can speed it up, okay? And so now at this point, I'm going a little bit faster. So that's what angular velocity or rotational velocity is. How quickly am I going through? How many radians per second am I actually changing? Okay, and the last one is acceleration. We're not going to work with that one too much until we get to the engineering option. But angular acceleration is basically how quickly is my rate of change of my angular velocity. So the same details that we use for linear works for rotational. We're not going to do a lot of rotational kinematics, but the same formulas apply with the simple letter substitution. So let's talk a little bit about uniform circular motion and what that means, okay? The two key words here are uniform and circular. Okay, circular obviously means that the object moves in a circle. The word uniform means that it moves at a constant speed in the circle. Not a constant velocity, okay, but a constant speed. The reason I say not constant velocity is because the direction is always changing. Okay, it's not, just going upwards. It's not going right, left. It's going in a circle. And because my direction changes, I still have an acceleration. I cannot say I am in equilibrium. Okay, so let's take a look at what's happening. Okay, in this case, I'm going clockwise around the circle, okay? Here's V1, and here's V2. Okay, so which is a little bit later in time. And they're equidistant around that top of the circle. Okay, and if I look at that, then my velocity vector is the same length. So the acceleration, remember, is change in velocity over time. So if I look at the change in velocity, okay, that's what this diagram over here is. That's the change in velocity over that period. Okay, and if I do the graphical subtraction, it's clearly going to point straight downwards. Okay, so it's V2 minus V1. And the result of that is an acceleration that is just straight downwards. Or since I'm at the top of the circle, it points towards the center of the circle. Okay, and that's the key, okay? Centripetal acceleration always points towards the center of the circle. That's actually what centripetal means. It means center seeking, center pointing. Okay, And the magnitude of that acceleration, we're going to use this formula that says the magnitude of the acceleration is the speed squared divided by the radius of that circle. Okay. There's a couple of things we know because to get to the other formula that was shown, and that is that the speed is distance over time. Since period is the time it takes to make one full circle, and the distance for one full circle is circumference, the speed basically comes down to simply 2 pi r over period t. Don't forget to use this method of calculating speed at times. Making that substitution for speed, okay, my acceleration, centripetal acceleration, becomes 2 pi r over period squared divided by r. After a little bit of algebra, I end up with that other formula that was shown in the beginning of the slides. Okay, 4 pi squared r over t squared. Okay, how do I get back and forth from the linear to the rotational variables? Okay, there are 3 bridge equations, and they're all pretty much the same. Okay, using the various letters, okay, where displacement is equal to theta r, okay, velocity is equal to omega r, acceleration is equal to alpha r. Okay, if you think about it, this is just basically the circumference equation. There are 2 pi radians in a circle. Okay, so if I wanted to know what the circumference is, I just multiply 2 pi times the radius. And that's where this equation comes in. Okay, all of the other equations pretty much follow from there. And this is the one that is actually given in the data booklet. Okay, velocity is equal to omega r. But if you ever need to, all of the rotational variables are just multiplied by the radius r to get the linear variable. Okay. It's important to note, though, also that the rotational variables will be in radians. Okay, it's 2 pi, it's not 360. Okay, don't use degrees. Be careful, understand how to change the mode of your calculator so we can go back and forth, but make sure you know when you're in degrees, make sure you know when you are in radians. Okay, so in rotational form, in linear terms, I'm sorry, centripetal acceleration is equal to v squared over r. We've already covered that. Okay, in rotational terms, we're going to make a substitution that says v is equal to omega r. And making that substitution, we end up with the other format that we've seen that says centripetal acceleration is also going to equal omega squared r. Okay. So centripetal force, not crazy about this term, okay, because when we say centripetal force, a lot of times we want to add that to our free body diagram and label it force centripetal, force sub c. The problem is that is really, 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 really bad. Okay, never, 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 ever label a force and call it centripetal force on your free body diagram. The reason we don't want to ever say that, label it, is because it's not a force, it's the net force. Okay, this is the final acceleration, the net acceleration times the mass. So we have to avoid using the term centripetal force as an actual force. You do know you're in the camera, right? So even worse would be to use the term centrifugal force. Okay, if you use the term centrifugal force, the IB graders are going to think you don't know anything and will just mark you with a 0. So never use that term. Okay, the last thing I want to cover is non-uniform circular motion. Okay, not all circular motion will be at a constant speed. In particular, things that are moving in a vertical circle, okay? So it's going up and down and up and down and up and down, okay? And in this case, I have the net force is going to be the vector sum of the gravitational force, straight downwards, and the tension force, which is basically just the string or whatever is holding it into the center. Okay, the net force is not always pointing towards the center of the circle. Especially at points like B and D, it's going to be pointing at some angle. Okay, only at the top and bottom, okay, points C and A in this diagram, does the net force actually point towards the center. And those are going to be the points that we're going to analyze the most because the analysis is pretty clean. Okay, thank you.